I must tell you something. Look, at the same time as Einstein developed his general, I'm talking now about general relativity theory, right? At the same time as Einstein developed the general relativity theory, a number of less revolutionary, less radical, less general and less deep, I would say, theories were suggested to explain what was known about empirical data at that time of these effects of general relativity. The scientists were able to measure a very, very subtle effect, namely the effect of the gravitational field created by the rotation of the Earth. So it became possible to measure this effect, which is of the fourth order of this gravitational constant, proportional to the fourth degree of the gravitational constant. So small it is. But it was measured by observation of the satellite movement around the Earth, right? And it turns out that it was in complete agree with Einstein's theory, but not with other versions. You
and that's
understand?
what made it stand out.
And I would say that only now we know exactly that Einstein was correct.
How are you, Professor?
Hello.
Pleasure meeting you.
Great to see you.
Great to see you.
Information theory, and now they call it quantum information theory,
Right.
actually.
Yeah, which is really the main interest of.
Well, before, in 1948, this publication in
Information theory in 1948 is when it started?
Yeah, he published. The point that he did it during the Second World War, and the work was classified, and only in 1948 it was published, you know.
Was it classified because of right after the war?
Yeah, because it has a lot of application in military communication and control systems.
Cryptography, no? Not so much?
Sorry?
In cryptography as well, or?
Cryptography also, of course, right. In all these areas. Coding, noise-resistant communication, and cryptography, of course.
What would you say because again, you worked very broadly, both in the quantum computation space, the connection between quantum information and physical matter.
Right.
And and you're known for. Can you talk a little bit about the work that you are the most known in that field?
Well, paradoxically, the most known, the most popular of my works was not exactly in the field of information theory, Shannon's information theory per se, though I did a lot of work in this area. But the most popular what it became, it was my work together with Norm Margolus. Norman Margolus is a brilliant guy who works up to now in MIT. I think he works as I don't think, yeah, he continues. I saw some of his recent publications, you know. And another guy whom I collaborate with was Tom Toffoli. Also a very interesting figure, absolutely talented, broadly talented in different fields of very creative and clear minds, so to speak. Yeah. And it's an example of injustice of our higher education system, university system, that instead of becoming a professor, maybe distinguished professor of the university, he was not given tenure, you know, and had to leave. And now he's just like a research associate or something at the Department of Physics of Boston University.
So
before he worked many years in MIT as a researcher, and then he worked as the associate professor, I believe, at Boston University. But they denied tenure. Very unjust, you know. Very.
So what happens, by the way, when they deny tenure for somebody? They can never reapply, or they can't reapply if they deny a tenure for them? Too political?
It was not for scientific reasons, basically. I didn't understand even the politics behind that. But somehow he's a different guy, you know. He's, for example, his manner to instruct, you know, as a teacher is kind of different, you know, from others, you know, and all that. And so, you know, I think it was unjust very much. We published together about a dozen of publications in best journals and all that. And when it came to his evaluation, I remember like somebody wrote, because I could read all his papers because I was involved with that process, right? But unfortunately, my voice was kind of isolated, you know. Yes, he published a lot of papers with Lev Levitin, but Lev Levitin is a very known researcher in this area, and TOEFL just started, you know, they kind of denigrated his role in that, you understand, and all that, which was really...
You really care about this, don't you?
Yeah, because he's an excellent human person, you know, and since the time that we knew each other, and we knew each other from 1981, there was the first conference on physics of computation in MIT, by the way, organized by MIT. You know, so we were very close in our interests, in our understanding of very subtle questions of what is the meaning of entropy, what is the meaning of information, how the evolution of physical systems in time takes place, and all that. You see that? So, yeah, I'm just mentioning his name because he played a certain role in that, and indeed we published together a lot.
And by the way, when I search your name, or even if I ask ChatGPT, he's mentioned. He's mentioned quite a bit. Like
yes, people outside of BU, you know, mentioned it very much, and he has a lot of references and all that. He is very well known. Before he entered that field, by my introduction, so to speak, I introduced him to physics of computation, physics of information. But before, he did work on reversible computing, and he invented that classical Toffoli gate. It's a reversible information process, logical information processing gate, such that knowing the results, you can restore the data, the initial data, you know, which usually, in usual...
I'm going to move closer to you so I can hear you. The cars make it hard to hear.
In usual process of computation, the data are lost, you know, you have only the final result.
Right. So he was working on reversible computation.
Yeah, he was working on reversible computation. He's a classic in that field, and Toffoli Gate is such a name that sticks to that. And,
Yeah.
You can ask everybody who works in the area of say automata. Also, he is known by his papers on cellular automata. That imitate some computation and all that. So he's a great guy, and unfortunately his academic career absolutely does not correspond to
reflect what his
to
actual
his
contribution was.
real work, to what he did, and his intellectual level, of course. This is kind of, unfortunately, this is not a single example, and somehow very intelligent and able people, and even productive people, they are not recognized enough, especially by the institution where they are recognized outside,
So that you're saying it's pretty common that because of political reasons or disagreements about ways of doing things, people get pushed to the side in academia?
I'm a little bit of exception, but I would say that I was just lucky, maybe.
Why are you an
becoming a distinguished professor, the highest possible level, and I'm a life fellow of IEEE, which is the highest degree, the highest membership level, right there, and so on.
That is interesting. Wow.
But
I see that it really it sits with you, like it.
But it just must be. It may be a matter of luck, I would say, because people try to promote themselves. Just every paper, every person like that, unfortunately, he thinks first of all how to promote himself or herself, and they did such things. For example, one of my acquaintances, I would say friend, but friend not in my meaning of the word, but in the American meaning of the word,
Yeah.
Like, you have thousands of friends on Facebook and things like that. Yeah, So that friend, he is also a researcher in an area which is close to that.
But did
computer science and engineering. He tried to organize 8 times. 8 times he tried to organize becoming a fellow, right? To becoming a fellow, you need a person who will nominate you, who is a fellow already, and nominate you, and also up to between 5 and 8 fellows who would recommend you, send recommendation, Only that you can become a fellow. So he tried it 8 times, and every 8 times he did not get it, I wrote a good characteristic good recommendation for him, but it did not help. Indeed, maybe he is not of that caliber. But I must tell you that looking at the list of fellows, I see that there are absolutely 2 different groups. One group, the people who indeed must be fellows, and the other people who organize it for him, for themselves. You understand?
Yeah. So
it's absolutely.
So you're saying it's more of like a boys' club?
Not, I would not say so. No. It's how to say it. Not. I don't want to say that people who are elected fellows, they are without merit. But it's a question of caliber, so to speak. Caliber of what they did.
Oh, what they did.
Of what they did, the caliber of things what they did.
But you're saying that some individuals, despite the caliber of what they did, still don't achieve certain accolades, right?
First of all, many individuals, despite of the caliber, are not, right?
Yeah.
Not recognized. and it happened sometimes by, you know how I never tried to promote myself this time, you know, this way, you know, so, what happened with me, it's only by chance. For example, how I became fellow, I'll tell you. This is kind of strange. Oi,
Oh, it's okay. It's okay.
I'm sorry.
Oh, you're good. I'll put it right there.
I was on an international conference on information theory,
Yeah.
and so we, a group of us, you know, people, the participants, just was standing and talking, and somebody said to me, there is going to be a meeting of the fellows of IEEE in information theory. Are you going to the meeting? I said, no, you see, I'm not a fellow. I wouldn't go to the meeting. How come? People were absolutely, you know, stunned, you know. How come you are not a fellow? Immediately, a few people wanted to nominate me there, you know. And indeed, I got like 8 people who wrote brilliant, you know, guys who wrote recommendations, and I was elected without a single vote.
Wow.
You know, and from the first time.
So would you say that you think, obviously you can't know for sure, but do you think that in history also, you know, the big names, Schrödinger, Einstein, a lot of the size of the recognition was luck?
But I would say yes, you know, even in the case of Einstein, I must tell you, you know, somehow it happens that it was such a period of revolution in physics that physics actually encountered difficult question, difficult that physics could not answer, you know. Physicists were kind of in a sort of
Dead end?
not dead end, but how to say, what is the right English word? In sort of a confusion, I would say, you know.
Really?
What to be, because
please correct me if I'm wrong, but wasn't
Yeah.
the impression towards the end of the 19th century that we're kind of done with discovering everything there is to discover, and it's only a matter of making it more accurate to
that
some
was
decimal
an
point?
impression for some, you know, people at the end of that. And you know this famous episode when Planck came to his teacher. The teacher said, why do you want to do physics? It's already closed area, you know, like that, you see. But then a number of things were discovered which were very contradictory. They didn't satisfy the views which were there, so they started to invent all kinds of this ether, you know, theory and all that, you know. But it did not work. So yeah.
Would you say?
Yeah.
Sorry, go ahead.
Einstein, of course, is the greatest genius of all times, and you know, the only person to whom I can compare him is Newton. Of course, you know, those two, you know, Newton, really. Yeah, but nevertheless, in his recognition and how to say this, that he's so famous is a part of luck too, so to speak, part of a lucky coincidence of situations, I would say.
Yeah, because
you know.
what he was, if I'm not mistaken, his Nobel Prize was on the photoelectric effect, right? It wasn't even about...
Exactly, yeah. You know, they were so cautious about that. Even at that point, you know, they did not want to openly recognize what he did in relativity theory, you know. They recognized his paper on...
So do you think it was because it was too controversial?
It was too revolutionary. It was not, you know, it was not controversial because no real physicist in sound mind could reject it, you know. Those who rejected were, you know, very second order people, mostly for other reasons, like why he is a Jew, and you know all that.
Yeah.
You know, so of course, all the physicists, they kind of accepted that, you know, but it was very revolutionary, you know, at that time. And you know what? I must tell you something. Look, at the same time as Einstein developed his general, I'm talking now about general relativity theory, right? At the same time as Einstein developed the general relativity theory, a number of less revolutionary, less radical, less general and less deep, I would say, theories were suggested to explain what was known about empirical data at that time of these effects of general relativity, affects the change of the perihelium of Mercury, right? You know, and very small effect, but it is observable, yeah? And deviation of the ray of light when it goes close to sun, you know, the big changes the direction. Yeah.
So basically,
but
for the layman, the difference there was that Newton's equation were not adequate to explain why would the light appear to be in a different place where it's supposed to be. You have to have relativistic effects
right.
for that to happen.
By the way, special relativity explains half of this effect. And general relativity just give the double value of that effect, you know. But those were, here I should say the following, there is some subtlety here. You know, every fundamental field, we know now 4 fundamental fields, as you know, yes, fundamental. Every fundamental...
The weak, the strong, the electromagnetic, no, the weak, the strong, gravity...
Weak, strong, electromagnetic and gravitation. Yeah. Okay, so each of them is characterized by a dimensionless parameter. Dimensionless, it means that it does not depend how you measure it, it's just a number, you know. And this parameter, for example, for electromagnetic, which is the best known theory, you know, this is quantum electrodynamics is a wonderful theory, I must tell you. When we could measure, say, 6 digits after, you know, the 6 digits, it gave the results with accuracy 6 digits. We measure with 8 digits, it gave 8 digits, 12 digits, still all 12 digits. We do not know where is the end of that, where it becomes. Every theory must be limited, yeah, somewhere. But about quantum electrodynamics, we still do not know. We know
even in Planck scale, Planck scale would be the end of it.
We did not achieve, say, Planck's energy. For example, Planck's energy is 10 to the power 19, I believe, giga-electron volt, you know, so it is, you know, not...
Quantum electrodynamics, sorry for the ignorance, was that Feynman, or...?
Yeah, Feynman is the last, how to say, the last
relic.
Classic in this field, you know, indeed. Okay, anyway, that constant, as you know, of course, it is the famous alpha, 1 over 137 approximately.
1 over 137.
37, of course.
Oh, 1 over...
You have a lot of...
Isn't it 1 over 137? Yeah. It's 1 over 37?
1 divided by 137. 137, yeah. 137, all that. Gravitational constant is very small. It's 10 to the power minus 43 or 47, I don't remember, but very small, right? Now, when you try to calculate the effects, you have to, how to say, what is the English word for that? My goodness. from time to time I forget, to develop a series. How you say
To cluster? Or?
to how to say when you create some quantity you express as an infinite series of terms.
Oh, a set? No?
Okay.
Okay.
So you express it in such a series of
Wait, when you isn't it? Are you talking about taking a limit of something? What do you? I want to know specifically what you're referring to. You taking an infinite terms of sets. So
you have a quantity,
Right.
which you cannot calculate exactly, but you can develop a converging series of terms.
well, it's basically, isn't it the basis of all calculus? Basically, isn't it the basis of all calculus of taking limits? Isn't it the same process?
Of course, but no, one thing is taking the limit. This is a way to make calculations when you do not. It is hard to find an exact result.
Okay, we're gonna do. You're not talking about group theory or set theory, right? Something else.
What happens with me that I forgot the term? How to
It's okay. I'll find it
how
later.
to develop a series. Develop the something. Forgot the term.
We'll find it and I'll put on the caption. Yeah.
Okay. Okay, so you have to develop such a series where this numerical dimensionless constant comes in powers, right?
Comes in?
In powers, different powers, right? Значит, first term, 0 power, second term, maybe, say, the first power, or maybe not. In some cases, you may have only even powers, so the second term will be already second power of that, proportional to. If they say alpha, so it's alpha squared, proportional to alpha squared. Next one will be alpha to the power 4, right?
Exponential.
And yes, and if alpha is a small value, you understand that they become. Okay.
Thank you. Appreciate it.
Okay, so the point that up to when was it done? It was done quite recently. I believe it was done already in the 21st century, after 2000, these experiments. So up to that moment, the only effects which were calculated were of the second degree, of the gravitational constant, right? Of second degree. But in parallel with Einstein's theory of gravitation, right? There existed a few more theories which gave the same result for the second degree.
And they were not based on the field on field equations. They were based on some other.
The different assumptions, different things. Not as deep and as general as fundamental. They try to, because the effects are small, they try to make small changes to.
Was it more associative versus explanatory? Would you say? Like they try to make small associations versus explaining the bigger picture.
Exactly. They make some, but you understand, though Einstein's theory was accepted, but it was not clear. Maybe there are some other theories which explain it very well, or maybe even better. Who knows, right? If you go to higher degrees. So only. That happened quite recently, maybe, I don't remember, maybe 20 years ago or so, the scientists were able to measure a very, very subtle effect, namely the effect of the gravitational field created by the rotation of the Earth. Of the Earth.
Of Earth.
Yeah, of Earth, right? Please understand, it's not a gravitational field which is created by Earth itself.
By the mass, but by the actual spin.
Only by the rotation.
How do you differentiate? That is.
Well, because you know the effect of that one,
Right.
You know you very well. But because Earth rotates, right?
Yep.
And that means rotation means that it's a non-inertial system of not an inertial system of reference, right?
Right.
Frame of reference, and not inertial frame of reference, according to Einstein, creates a gravitational field, which is not given by other theories, right? Like that.
I see. Because motion is the same as mass, basically.
Yeah. So it became possible to measure this effect, which is of the fourth order of this gravitational constant, proportional to the first degree of the gravitational constant. So small it is, but it was measured by observation of the satellite movement around the Earth, right?
Yes.
A very, very subtle one. And it turns out that it was in complete agree with Einstein's theory, but not with other versions. You
And that's
understand?
what made it stand out.
And I would say that only now we know exactly that Einstein was correct, you know.
Because of
before it
GPS.
could be always, you know, a shadow of doubt, you know.
So let me ask you something about that through the lens of your expertise. Do you think that Einstein had any way to... So first of all, before I ask that, how do you view computation as a fundamental thing in existence, or do you see it as an arising property of what matter is doing under certain conditions?
Well, it depends. It depends how you define computation. You know, after all, you can interpret everything what is going on, whole process is a certain computation. Nature computes its next state, having the present state.
Right.
It must
I see what
go
you're
to
saying.
the next.
So you can call it computation.
You can call it computation.
So let me ask you
And-
something more specific then. I understand what you're saying.
Yeah.
For example, you mentioned cellular automata, right? So I've had this conversation recently with a physicist who came from string theory originally, and we got bogged down by this point because I was telling him, Mo, please help me understand, because so the game Conway's game of life, right? Which is one type of cellular automata. I'm going to make a statement, and you correct me if my statement is wrong. Is it not the case that there is nothing that dictates this very complex behavior aside from mathematical... But no, it's not even mathematical logic. It's just these four rules, and somehow it gives rise to this stable complexity under certain initial conditions, but it's not based on anything, any physical underpinnings, right? So it's happening in the physical world on a screen, and of course, and it has certain interactions with the physical matter in order to create a computation, but the content is purely based on these rules that seems to be decoupled from what the physical world is doing. Would you not agree with that?
Sorry, I missed the last phrase because it was so noisy.
Sure. So the fact that the game of life works, Conway's game, and there's all this complexity that arises, doesn't it show that there's some fundamental rule that is prior to matter itself that it follows? Does it not translate to that for you?
Well, you see, some people, and I believe that maybe even Tom Toffoli himself, you know, sometimes they expressed a sort of a view that computation, the world of computation is prior to the world of physics.
Right, it for bit. I think it was Wheeler, right, originally? The concept of it from bit.
My point of view is more cautious about that, or more traditional. What I think that I follow, like Rolf Landauer, another very interesting person in that field, said once he said information is physical, such a meme, so to speak, or meme, how to say it, meme. Information is physical, and I believe that computation is physical. You cannot, to understand computation, you cannot consider it differently as a physical process, right?
So it has to have basis.
Though, just try to finish that phrase,
of course.
Though computation sometimes can be described without any reference to physics, just by logical formulas, Boolean algebra and things like that. In fact, if you try to look how you can implement it, how it can be how it can be implemented in the reality, the embodied, so to speak. The embodiment of that is necessarily physical, and the fact that it is physical puts certain conditions on what can be done and how it can be done. And that was actually the basis of all my work for many years, right?
I know, yeah.
And I would say that the last important, it was not last for me, but many people look at that, step in that process of combining that, the put a bridge between computer science and physics was just that what people call Margolus-Levitin theorem, right? Which of course.
Yes.
Yes.
So let me recapitulate what you said to make sure that I understood you correctly. You're essentially saying something very well. You predate David Deutsch, but David Deutsch is known to also talk about this quite a bit, which is that ultimately computation is a physical process. And I guess what I'm expressing is more the sentiment that, of course, that when computation occurs in the physical world, it has to be follow what the laws of physics allow for. You can't do anything that you can't compute in a way that will break the laws of physics. So in that sense, it has to be based on the laws of physics. Would it be accurate to say that whatever physics is, it is also computational? Would that be a phrase that you're comfortable with?
Again, I would have to say that it depends how you define what is computation. As I said, you can consider everything that goes on in nature is computation of the next state of the nature having the present state according to certain rules, to physical rules. Indeed, physical rules dictate what would be the next state after you have a present state.
I guess I'm alluding to the content. Because, for example, a simple example is that the content of the game of life appears to be ordered to an observer, and that order seems to be orthogonal, orthogonal would be the right word. It seems to be orthogonal to the physical process that gives rise to it. Like it seems to depart, it has its own reality, even though it's happening on a physical substrate.
Yeah.
The content of it to the observer seems to be decoupled from it. in a way that there's nothing in the laws of physics that dictate that it needs to, if you follow these simple 4 rules, you're supposed to get these very complex structures. You see what I'm saying?
But before it works as a cellular automata. This game of life is a cellular automata, right? Before you have that cellular automata playing that game, developing in time, you have to create a physical system that would, in such a way that would follow that process, right?
Yeah, it must be based on physical.
You create such a system such that the physical laws of that system determine that it will go this way.
But there seems to be a lack. There seems to be a whole. There's no explanation as to how it jumps from being this thing on a system, and then instead of being chaotic, if you follow any other 4 rules, it develops completely differently. But if you follow the specific 4 rules,
right,
then it does that. So why, the explanation as to why it's these 4 rules that give rise to this exact structure to me seems to be orthogonal to what physics is doing. Is that incorrect in your view?
I do not feel that it's orthogonal or independent of physics. I do not feel it. After all, because it's a natural process, there should be something in the physical conditions of the process that would determine it.
I agree, but that's something. I guess I'm saying that it is not yet known what that something is. I agree. Of course, there has to be. It's not magic. Of course, there's something. Obviously.
Yeah, it may very well happen because we know so little. It may happen that we do not know what is the connection.
I will tell you why I'm asking directly.
Yeah.
Because because your work is also very technical, departing into more esoterical and hypothetical trains of thought might be interesting, but less relevant to what you do and your expertise. But I do feel that this particular point drives an element that I think is being overlooked, and you tell me what you think about it. It seems to be reasonable if we look at the grand scheme of things, of evolution of things like us, because I'm sure we're not alone in the universe, but even if we are, the fact that we as humans, as computational systems, can do what we can do, and certain things are simply not possible without like the way we use computation, like phones and computers and spaceships and things like that, right? And all of these things originate in our minds, and they are computational interactions, obviously all underpinned up by the laws of physics. But if you run the clock forward long enough, if we don't destroy ourselves, which is a big if, but let's say we don't, run, doesn't matter how long, 100,000 years, 1,000,000 years, doesn't matter. Eventually, what was in our minds, in our computational system, will paint the galaxy, because our ideas, our engineering, our structures, our art will literally paint the galaxy, right? So here you have a firm example, if that happens, where the computation that happens in the species brain influences the physical reality in a way that there will be structures existing that wouldn't exist without that computational system. That's what I'm saying. So there's the ideas, everything will spill into what we call the physical world. It will instantiate itself. And I agree that at bottom it's the same process. I'm not trying to claim that there's some kind of a departure in that sense, but I'm saying there seems to be this extra ability that the universe possesses that we don't talk about, because it includes the observer, and scientists don't really know how to talk about the observer in any meaningful sense.
But it's a little bit of the chicken and egg problem, because the observer, the person who started or organized its computation, is a product of nature. So nature produced that, and this product produced more products, and so on, like that. So
no, you're absolutely right. I guess on a technical way, unless you have a theoretical framework of what the observer is, what consciousness is, then all of this is just speculation, because you don't really know how it arises, how it's influenced by and influences
Of course,
physical
yeah,
matters.
we do not know. Yeah, we do not know absolutely, and probably that lack of knowledge is not just that. Okay, today we do not know, tomorrow probably we can learn that. I think that it is existential, because the part of the system may not imitate all the behavior of the whole system. It cannot include information about the whole system.
Most likely it doesn't.
In particular, why do we have this illusion of a free will? It's illusion in my understanding. Why? Because what we feel as the state of our brain is not the full state of our brain.
Of course.
Right? We do not know the full state of our brain, therefore we imagine that we have a free will. Though of course it's dictated by the physical state of our brain.
And you're right, because it's the illusion of free will is fundamentally rests on the illusion of the self. The fact that we feel we're a singular agent that is operating somehow separate from the external environment, and that, like, versus being, I always have
the point that it is, there was even a theorem, by Kolmogorov and his students, the Kolmogorov, they proved that in order to imitate any universal, like Turing machine or any universal automaton, right, with n states, right, the system that imitates that knows everything about the state and predict the behavior, right, can pre-calculate the behavior of the system, should have n times log square n, like that, right?
Repeat it, n times?
N time multiplied times log n squared.
Okay.
Okay, so log n is small compared to n.
Yeah.
Even if you square it, it is still small, right? Nevertheless, is much less than n. So actually, you have to add not so much, but more than n. If you have only n, you cannot. A system of n states cannot know itself, and it cannot even know any other system of n elements. You understand? So it should have.
Yeah. I always have this. I had a funny thought one day, and I knocked down the broom by mistake. It was standing on the corner, and I thought, what if the broom thought, "Oh, I just felt like falling down." And that's essentially what I think is ultimately happening. But there is something, even if we don't have the agency that we believe that we do, there is something more novel and complex about the behavior of systems that can compute on the level that our brain can, versus systems that just bang into each other like physical systems.
Yeah.
I agree. Ultimately, there has to be some explanation, a thread that goes through all of them, of course. But what is that difference? This is why, when people talk about the difference between, even if you have the same physical elements, the way they arrange, i.e. the information in them, is what's determining its future states. This is the sense in which I'm asking the question, is information fundamental or more fundamental even? And of course, it's depending on how you define it, but words have to mean something, right? So but by physical, we mean the things that seem to just bang into each other, if we want to use like a very crude definition, right? They're just the constant laws of physics, and things just kind of interact. Versus a system that, in addition to this interaction, there's also an internal component of calculation of a flavor that nature itself does not have at its core, or it doesn't seem to be fundamental but arising, and that process seems to give rise to new and novel elements that even the universe itself could not inspect. Even the universe itself could not see it coming, so to speak. Right. And so let me ask you more concrete questions about your work. I read that in one of your papers you describe that the density matrix is what determines it's not a statistical calculation, but a density matrix that determines the probability of a quantum computer, right? A quantum computational process. Would it be fair to compare this density matrix to the fields in quantum field theory, or do you view it in a very different way?
No, density matrix is a general form of description of the state of the physical system. You see, quantum theory has a concept of wave function. Wave function, though of course if you come to quantum field theory, then even the concept of wave function is not general enough. You have to consider special, like C algebras and all that. But let's forget for a moment about that. Suppose we are just in the field of even non-relativistic, suppose quantum mechanics, maybe. But
would that be hidden variables, by the way?
Huh?
These extra elements is a kind of like hidden variables, or very different?
Wave function is the fullest possible description of the state of the quantum system. Okay. The fullest possible.
Okay, so there's nothing beyond that.
Yeah, and having that, you can get any information which is possible about the future development of the system and so on. Density matrix is analogous to the probability distribution, right? In classical mechanics, you may not know exactly the state of the system. In quantum mechanics, in classical physics, exact state of the system means knowing the coordinates and the momenta of all the molecules, suppose, or all the particles in the system, right? This would give you a fullest description possible. And but in classical physics, if you do not know the fullest description, you may have probability distribution. You do not know the exact, coordinate or exact velocity of that particle, but you may have distribution of velocity, distribution of coordinates, and so on. A quantum analog of that is density matrix. So density matrix is analog of the probability distribution.
Yes.
But because it's in the quantum world, it has some different properties, of course.
Different properties.
Some properties are the same, and some are different, you know.
Okay, I think I'm getting the picture. A couple of final questions. A fun one for the end. If you would have a student right now who you really, really like, what would be your biggest encouragement for them? What direction in that field?
In that field?
Yeah. Would you say quantum computers? Would you just like more theoretical? What would you encourage them to go into? Where do you see the future really yielding a lot of fruit?
There are some fundamental questions which remain kind of unsolved, actually, you know, without clear understanding. For example, one of them, I don't mention, you know, there are many, but one of them that I still only on the threshold of that. I did not try to, you know, to storm this problem. And it is really very challenging, would be, yeah. You know what is this no-go theorems in quantum theory, right? No-go.
No-go? No. You have to.
No-go. For example, you cannot copy, you cannot clone quantum state. The known state, of course, you can, if you know the state already, you have the wave function that describes the state. You can make another system into this, put it into this state, right? And so, of course, if you know. But if you do not know the state, just to make copy of that state is impossible.
in principle impossible.
In principle, impossible. You can try to make it to make similar to that up to a certain degree, but it will be always not such one, and you cannot come arbitrarily close. There will be always a big gap, so to speak, between that system and the copy. You understand?
Yeah.
Also, you cannot broadcast.
What does that mean?
Broadcast, it means that you have a quantum state, and you transmit that quantum
you
state
take
to
the same
somebody.
state and move it to another
Yeah, move it
as it
somewhere.
is. Because the second it moves, it
You
changes.
can do it, but not to a few, only
different
to
universe.
one. Yeah, to one, and you lost it. Yeah, that's it. You understand? You cannot reproduce it. You cannot. You can just lose it. Gave it to somebody, but you stay without that. You know, and cannot broadcast. You cannot even. Non-orthogonalization, it means that you cannot find a state that would be orthogonal to that one. Orthogonal, because wave function is a vector in the Hilbert space, you know, in infinite dimensional, basically. Yeah, and you cannot find a vector which is orthogonal to that. Though you have it
because it's in an infinite space.
why you cannot?
Yeah.
Or,
or because it's the sum of the full
look,
description.
if you could orthogonalize that one, right? If you could, you can produce a number of these orthogonal states, make a measurement, and then you know exactly what is the other state. You understand?
And again, I'm certain that I'm getting it very, very wrong, but please correct my misunderstanding here. Isn't the whole, like, aren't the Deutsch equations exactly the calculation to be able to allow quantum computers to do what they do through that principle, in which they spread the workload across parallel slices of worlds, and then the equations allow you to know what is the statistical probability of you being where you are in that entire array, and that's the certainty, the probabilistic certainty you have about what the calculation is. Is that not correct? So like you're saying that if you can create orthogonal states, orthogonal might be different than how I'm using it here, because it's a technical term, I understand. But isn't orthogonal just means perpendicular in some dimensions to the
yes,
other
it's perpendicular in the in the Hilbert space.
So as a simple question, isn't the whole point of quantum computers being able to do what they do based on us being able to do something like that? Or that's not the same at all? The principle is very different?
No, it's not that, no.
Okay.
The whole idea of quantum computing is based on the fact that physical transformation of any quantum system in time without noise, if you eliminate noise, absolutely no noise, is given by a unitary transformation. And unitary transformation does not change the angles between states, you know. It is one-to-one transformation such that it keeps all the information, so to
I
speak.
see, so there's a linear, okay, I see what you're saying. So it's not orthogonal because it's just, okay, I see.
So it is, it can go, you can make any angle of that, whatever, right? But the point that it's transformation that keeps all the information about the system.
I see.
Right? And the whole difficulty with quantum computation is that, unfortunately, it is so if you can isolate it from noise. But if you cannot, you know, then what happened is this decoherence process that, you know, erases the initial state. You have whatever noise, you know. It is very difficult.
So finish your thought. So that these problems, the orthogonal problem, would that be, what is the thing to work on here? Because if you're saying it's impossible in principle, or you're saying you would encourage your student to try and find out how to do it?
I don't understand I'm saying I don't understand, but I believe that nobody understands, you know. I don't understand why it is so. What is the... You see, there is a number of the such no-go theorems, right? Each one is its own theorem that can be proved properly and so on. But what is the underlying principle of that? You see? I guess in some way that its principle is conservation of information. You understand?
Yes.
Because any of these processes, in one or another way, would lead to gaining some information about the state of the system, which is forbidden. Quantum theory forbids that, right? The axioms of quantum theory forbids that, but it is not obvious. It's not obvious because quantum theory itself, it doesn't have the concept of information. It does not include the concept of information. So my goal is to include that concept into the quantum theory and prove that this concept, the conservation of information, is fundamental law that gives the origin to all the other laws. You understand?
Yes. Wow. Okay. That's a lot to...
But it's a challenging thing, you understand, and I'm not sure that up to the end of my life I would be able to do it, you know, because there are many other things that I'm involved with, many other scientific projects. Right now, for example, I have two of them going with my authors, my former students, you know. One of them is about... just to show you that it's completely different area, about interconnection networks in multi-processor computers, you know, processors communicate with each other and how to do it properly and all that, and what are the limitations. One, for example. Another is I'm with my former students invented a new type of learning automata, you know, that is supposed to have, you know, we try to make it working as well as previous models in stationary conditions, stationary environment, but also work very well in non-stationary, which other learning automata do not do, you know. They cannot do it.
Non-stationary would mean that the rules change also as it translates in time, or no?
No, yes, exactly. Yeah, exactly. You know that.
So the rules are dynamic.
Yeah, the rules. You know, for example, learning automata should learn what is better, to do this or to do that, and if it is stationary all the time the same, it's better to do that. You are more rewarded or less punished for doing that. You, after all, they should learn to do that. And they're doing that all the time, right? But like what if it changes? You know, you have quickly to adjust and so on.
Sounds like AGI. Sounds like Skynet. Wow. Professor, I want to really thank you for taking the time. I know that you.
Yep.
If you're willing to spend a few more minutes, we can sit. I don't want you to like.
Yes, I have some. You know, it's 25 minutes.
Yeah. Wow.
20 minutes.
This is such an invigorating conversation. Thank you. I was also.
I'm not sure that it is what you expected, because after
all I expected was for you to share your knowledge and thoughts. There was no real aim aside from getting your true opinion as an expert in the field. There was no. I'm not steering towards any particular thing. I just wanted to see what you really think
about quantum computing. I must say that. I'm a little bit disappointed with the development. Though I did not take an active participation during the last years in that, you see. But I'm disappointed in a way that, you know, no progress actually in quantum computing per se. To have a system in a certain set states and to see the development there are two difficulties. One difficulty is that there are not so many, maybe 2.5, as I say, algorithms for that. One of them is that algorithm which for the factorization of large numbers, right? And another is algorithm for search for a certain object in a large
space.
Large,
so do you think like protein folding would we be able to do protein folding with quantum computations?
I don't know, to be honest. I don't know. You see, but there is, first of all, there are not so many algorithms that somehow new algorithms for a long time were not invented, And another is that you should be able to get a quantum system which is two different things, which contradictory conditions. Once that it should be isolated from the other world, not to be sensitive to the noise, right? Mm-hmm. On the other, it should be controlled. You should have an approach to the system,
you need to
possibility to approach and to change the state. But if you have such a possibility, then the noise would have also that. You understand, which is difficult. Like that.
So are you saying that they didn't really make any progress? Like, are you saying that it's a little bit overhyped?
Limited progress. Yeah, limited.
And you don't see a way for it to have a breakthrough in that field? Potential way?
I don't know. The potential way, in my opinion, there would be that it should be done on solid state devices. Solid state that has quantum, what is called quantum holes or quantum. How it is said, quantum, forgot it. The states which has like that, it has like a hole in which it is, the quantum, the energy level is below zero, right? So it remains there and cannot go out.
Okay.
Its system. Quantum dots. I believe it is called quantum dots.
Dots. Okay.
Quantum dots. Yeah.
So that's one potential way forward. You're saying?
Yeah, I believe that mostly. What was done, people indeed very inventive. They tried to do it collectively on, for example, nuclear magnetic resonance systems. Were actually a full collective, not single. Not single molecule or whatever atom is, but the whole collective, and that's like that. Very inventive, but all with limited success, I would say, right? So this is one thing. So there are two difficulties on the development: lack of algorithms and lack of empirical possibility to do this, the experimental base. What was a progress? One can say, how come you have already this quantum with a number of companies are doing that? What they are doing is sort of a quantum analogous computation. Actually, they are not really digital. They have elements of digital, but it's rather like analogous. And analogous is always limited,
Well, you have to have some translation, right? Like, I mean, even with the quantum computation, you still need a regular computer to translate the data. We can't understand.
Of course, but
so there's a bottleneck there, but you're saying there's another bottleneck in addition to that.
Yeah,
okay.
I mean, there are two, as I said, right? But what I'm trying to say that there is a progress, but the progress in getting quantum analogous computation rather than purely digital. And with analogous computation, it is always the limitation that it is good only for a narrow class of problems.
You mean analog computation?
Analog,
oh,
yeah.
Yes, okay.
analog computation, you know. So the process imitates some other processes of our system, right? Like, for example, you can imitate the process of flying of a plane in the tube, you know, aerodynamic tube. So you understand something that, you see, or even in electrical, how to call it? Electrical, what is it? It's called, like with electrolytes, you know. It doesn't matter. Okay. Anyway, what I'm trying to say that this is not exactly what I would call digital quantum computing. And so I would, of course, hope and expect progress in that, but I do not see immediate breakthrough.
Yeah,
you know.
So there needs to be some change in the way that they're thinking about the problem.
It is very, how it's called, incremental.
Yeah.
I have a question. Steps,
I have a question for you out of left field, and I don't know if you'll be able to answer it easily, but you know the whole non-locality that was talked about in the last few years because of the Nobel Prize. Not the Nobel Prize. What did they won? The Nobel Prize? No, it was the Nobel Prize, right? In the non-locality.
Non-locality. Yeah.
You know, the phrase goes, even if you put the particles on the other side of the universe, there will be action, with like immediate action on both, right? How do they know that experimentally? How do they know that it would be true even if you put it on the other side of the universe? Do you know?
Well, the other side of universe, I don't know because we are not on the other side.
That's what I'm saying. But there's kind of like physicists repeat this.
But it is true even for any distance, whatever is the distance. It can be 1 meter or 1 kilometer or 10 kilometers or whatever.
It's always the same.
This is an empirical fact, of course. Yeah.
But how do we know that after, I don't know, 200 parsecs, all of a sudden it changes? How do we know that that's not the case? How do we know that when you go outside of some, distance, maybe because of some effects of whatever dark matter is, like, how do we know that it truly holds no matter what? Like, what is the empirical part?
We do not know empirical, but we do know theoretical.
Got it.
Because from theory it follows it doesn't depend on distance.
And if you want to assume that the laws of physics are the same across the universe, then, okay.
Yeah, because, if they are universal. By the way, of course, from time to time there are, and even outstanding physicists try to express the idea that maybe laws are not so universal, or, for example, changing in time, that these fundamental constants that I tell you, the
1 over 137,
the 1 over 137, and so on, change in time, but a lot of observed data shows that it is not so. That it remains
because
all the time.
Yeah, there's also one about there's some theory that hypothesis that states that the constant of the Higgs boson, the boson field, the Higgs field, seems to be maybe in a local minima, but it's possible that it would like either jump up or down. There's this hypothesis.
Well, you know what? The fact that we know so little, and as in the end of the 19th century, people believed that physics is all set,
Yeah.
So at some point, close to the end of the 20th century, there was such a sort of an impression that almost, I remember a paper published by one of the famous theorists, which is called Is it the end of the physical theory, something like that. But all of a sudden it turns out that the dark matter was discovered, and then the dark energy. And all of a sudden it turns out that all what we know relates only to 4% of the total energy or mass of the universe, right?
We're due for a
So
revolution.
we do not know anything. You know, it is so funny that actually it turns out that, and I must tell you that even things like you have heard about the standard model of elementary particles and all, up to now, no experiments contradict that theory. And one of the major predictions of the theory was that Gibbs, how it is called?
Supersymmetry?
No, that constant that was discovered.
The Higgs constant?
Yeah,
Higgs field, yeah.
constant. Yeah.
Oh, it predicted the Higgs, yeah.
Yeah, Higgs constant. So, and it's predicted, and it was found, not exactly the same value, but at least the same range of values, right? So it was a success. But if you look at this standard model, you see a number of particles, a lot of them, with certain masses. These masses have no explanation. Why it is this mass, or I should speak not about masses, but rather about the ratios, because what matters is dimensionless constant, not dimension, So the ratios, nobody knows what that. And it looks like one said that, look, the standard model in elementary particle theory looks like some botanics, like you have so many flowers on this species, so many of that, so many leaves on that, like description,
Yes.
rather than explanation.
Yes.
Nobody explained why it is so, why it is an open question.
And I believe it
Well-
will always be an open question. I really think that this idea that somehow we're going to have a nice tight bow that explains why everything to infinity seems to be not even plausible, because in order to know truly why, you have to be outside of existence, which by definition is, like, you can always ask, okay, but what's outside of that? But why this, right? So I feel like we will always be playing this infinite game of why, which is great. It's awesome. It's fun. But you don't think so?
But on different depths, I would say.
Sure.
For example, what I'm trying to say that about electromagnetic events, we know, so to speak, everything. Everything can be pre-calculated, everything could be and observed, and everything in a very good agreement with all that, you understand? It is like that. But when it comes to strong interaction, okay, we do not have such a great underlying theory first, right?
It just
the quarks explain something, but again, it's a matter of description rather than of explanation, this is one thing. And the other difficulty is gravitation, though we have excellent, as you know now, really correct theory, Einstein's genius guess, or what is it, right? It was just a genius guess. But nevertheless, it is not integrated with quantum theory, and nobody knows how to do it. There are different attempts, but no attempt was successful, right?
What do you?
So the situation is indeed
One final
that
question.
may be a stimulus for people to
Yeah.
go into this field and to try to find something.
I really hope
Yeah.
that will be the case. We need more scientists and we need less people in finance.
Yes.
One final question for you. From everything you've done in your life, what was your favorite either project or field that you interacted with? Was it in this field of information physics or something?
Yes, yes. You see, that it happened that I was one of the pioneers, how to call it, in quantum information theory. My first paper in that field was published in 1963.
Wow.
You see, so it was.
Was that in America already?
No, that was published in Soviet journal, And my first paper in English, in information and control, that was brilliant journal. At that time, information control was published in 1966. And do not ask me how was it difficult to get a permission to publish an American journal. I was in the Soviet Union there. It was not,
I can only imagine.
Yeah. I wanted to get into correspondence with J.P. Gordon, who started also research in that field. His first paper was published in '62, and that paper partially overlapped with my paper published in '63, in the beginning of '60. Of course, they were absolutely independent, these two papers, right? But I wanted to get in correspondence with him. I was forbidden to do that,
Wow.
Well, I was told that I have to get a permission from the presidium of the Soviet Academy of Sciences, which is a bureaucratic organization, you understand? I came there and I talked to that bureaucrat, and he said, no, I do not recommend it, don't do it. I said, why? And he answered, because he is a shark. You understand? He's the shark of imperialism,
Wow.
Then when I came to the States, I met J.P. Gordon. He was the head of the quantum electronics department and at the Bell Systems company, right? And he was the head of the department, And I told him that. He said, yeah, well, I'm a shark.
Wow.
You understand?
Yeah.
So I wouldn't tell you how much effort was for me that they would allow me to publish that paper.
It is crazy how life also imposes itself on matters that seem to be very straightforward.
Okay,
Lev,
so
Professor, thank you so much for spending the time with me. I really appreciate it.
How many years it was? 60-something, right?
Wow. In one field.
60-something years ago.
So one can say that you know what you're talking about. Thank you so much.